Now we're going to consider valence electrons. They are found in the outer shell, and we don't count electrons in the d or f orbitals, where the d or f orbitals are already full. Let's take a look at an example. Here you can see that the first shell, the second shell, and the third shell all have electrons, but the first and second shells have filled shells. The third shell does not. It is only partially filled. Now, the outer shell is the third shell, so the number of valence electrons here in silicon is 4. The first and second shells get ignored. They are inner shells and are never involved in reactions and are not responsible for creating bonds between atoms. The outer shell, however, is both involved in reactions and used to create bonds between atoms. So, we need a good understanding of the outer shell. We use the octet rule that states an atom can gain, lose, or even share electrons with another atom for the purpose of obtaining the number of electrons found in the nearest group 8 atom, including helium, neon, argon, krypton, and xenon. Now, this is almost like saying achieves a filled shell, but be careful. For the first shell and the second shell this is true, but the third shell onwards, note argon for example, is not a filled shell. 3s, 3p are filled, but not 3d. So, this is why the octet rule definition is around the electronic configuration of the nearest group 8 atom. However, the octet rule starts to significantly break down in the third shell anyway. To fulfill the octet rule, atoms can give or take electrons that result in an ionic bond. If we use the method of sharing electrons to achieve the same number of electrons as found in the nearest group 8 atom, well then we are creating a covalent bond.